The nitty-gritty of radicals here in chapter 25. We've gotten the basics down from mini lecture 1, kind of the electron movement and the elementary steps. Now let's look at the classic radical reaction, that being free radical halogenation of alkanes. It's kind of interesting. Alkanes don't do anything, right? We ignore alkanes. We've got all kinds of ethyl and isopropyl groups that we just generally say forget about them. They don't do anything. Well, that is unless you're trying to start your car. Alkanes combust. Yay, fossil fuels, right? However, we're about to see that under the right conditions, we can take alkanes and expose them to a little energy in the form of light or heat, and hey, we can get a halogen to add. In other words, we whip off a hydrogen and put a halogen on. Maybe we put 2 halogens on, and so on and so forth. So how does this work? Well, as you can imagine, it is not a polar mechanism. We're not talking ions here, we're talking radicals. It's a chain reaction made up of 3 steps. Initiation steps. Well, in the initiation step, you start with perfectly seemingly unreactive molecules like an alkane and a halogen. There are no radicals, but then by treating those reagents with light or heat, you get radicals. Once you have radicals, they can react to form more radicals. That's a propagation step. And then the reaction comes crashing to a close by a termination step when, for example, 2 radicals combine or couple to terminate the reaction, ending up with nothing reactive on the product side. No radicals. Alright, so in great gory detail, if I hit molecular bromine with light of the right wavelength, I can homolytically cleave that sigma bond quite readily to give 2 bromine radicals in an initiation step. Upon getting a bromine radical, it can then undergo a reaction with my starting alkane, in this case cyclohexane. And since it's a radical reaction, we use our little fishhook arrows. And again, I am just cleaving that bond, that sigma bond, right in half. Homolytic cleavage there. And that will give me a propagation step whereby I end up with a cyclohexyl radical and HBr. So this is called H-atom abstraction, or in Carty speak it would be the elementary step of SH2. Well, once you have the cyclohexyl radical, you can imagine that it's very straightforward for it to pluck apart the bromine bond and get brominated, giving you the product. There's my cyclohexyl bromide. And again, this is a propagation step because the secondary product is another molecule of the bromine radical. So those 2 steps are propagation. How does the reaction end? There are innumerable termination steps. One, for example, would be the rather unlikely happenstance of a bromine radical just happening to find a cyclohexyl radical, but that can happen. Or 2 bromine radicals combining to regenerate molecular bromine. Now, as you've noticed, I'm sure, Carty has table upon table upon table of bond strength data in chapter 25. But what I want to point out on this table is how much weaker the sigma bonds are for these kinds of molecules that undergo radical reactions. So, for example, bromine, chlorine, fairly low energy sigma bonds. And my gosh, look at the peroxide. Wow, 30 kilocalories per mole. That's kind of amazing. Whereas typical carbon-hydrogen or carbon-carbon bonds, they're a lot stronger. So that's why it works to do radical chemistry. You just need enough energy in the form of heat or light, and you've cleaved a bond and you have a reactive intermediate, the radical. The deal is, though, free radical halogenation of alkanes does not work for all halogens. Iodine just doesn't do it. Fluorine, holy moly, does it pretty well. A little bit too well, if you know what I mean. And if you want to know more, just click on that YouTube link. And it's very important to understand that there's a selectivity issue. After all, we've got lots and lots of hydrogens on these alkanes. I got CH3 here, I got a different CH3 here, I got a CH2 here, I got a CH here. So needless to say, I could pluck off any one of those hydrogens to get the halogenated alkane. Furthermore, I can get dihalogenation, I can get trihalogenation, I can get a holy mess when it comes to free radical halogenation of alkanes. So, one of the important things about chapter 25 is understanding Hammond's postulate and how it applies to the selectivity of free radical halogenation. A good little exercise for you in the meantime, good little review exercise, is to think about what are those four possible isomers I could form from the monohalogenation of this particular alkane. Which ones are chiral, and I've got another addition which will make it even more fun. Predict the proton NMR for each one of those four possible isomers. That would be really good practice. Okay, so selectivity. It turns out that bromination is tons more selective than chlorination. Why? When I take that molecule, the alkane, let's see, what was it, 2-methylbutane, and brominate it under free radical halogenation conditions, I get almost exclusively 2-bromo-2-methylbutane. Chlorination, not so much. Why? It's all thermodynamics. Okay, it's all thermodynamics and the stability of the radical. So here's the elementary step that's the key product deciding step in the mechanism, formation of that reactive tert-butyl radical. When I look at the energetics of this elementary step, the heat of formation of 2-methylpropane is 381 kilojoules per mole, and the heat of formation for either HCl or HBr are shown on the right. Now if you compare those two enthalpy values, you'll see that now we've got a distinct difference between chlorination and bromination. In other words, we're going to ignore this guy because we're forming the exact same radical whether or not we use chlorine or bromine. But by comparing HX to 2-methylpropane and comparing those enthalpy values, we can see that for abstraction of a hydrogen by the bromine radical, it's endothermic because we only get 364 kilojoules per mole back when we pluck off that hydrogen. It's exothermic for chlorination. So what? It really makes a huge difference because bromination means endothermic, which means the transition state is going to be very radical-like. So here's the energy diagram that correlates to that statement on the previous slide. It's endothermic. Here's my starting materials. Here's the products of that elementary step. Because it's endothermic, by Hammond's postulate, the transition state right here leading to the formation of the tert-butyl radical has a ton of radical character to it. So that's because, my goodness, if you just think about it, that bond, the hydrogen bond being pulled off of the tert-butyl piece, is fairly fully broken. So as the reaction proceeds, and this is such an endothermic step, there's a whole lot of radical character built up on the tert-butyl piece, and really not very much radical character associated with the HBr. that difference means there's going to be a huge difference in the energy barriers between forming a tertiary radical, as shown here, versus plucking off, say, one of the methyl hydrogens to form a primary radical. So since there's such a huge energy barrier difference, I get great selectivity. Look at the difference here. So chlorine, not such a big difference in the energy barriers. Bromine, a huge difference in the energy barriers, and consequently a humongous difference in the selectivity. So if I try to chlorinate 2-methylbutane, I get a nasty mixture of isomers, but when I brominate it, I get nearly exclusively abstraction of the tertiary hydrogen and formation of 2-methyl-2-bromobutane. So that kind of wraps up free radical halogenation. Just remember that synthetically it's very useful in that you can turn something that's generally inert, an alkane, into something pretty useful, an alkyl halide. But it's not necessarily selective. And what does this have to do with the price of tea in China? Well, it's all about this juggler. This juggler was going to his next performance, and the police pulled him over because they thought he was speeding. So the policeman noticed that there were an awful lot of knives in the juggler's car. So needless to say, he was a little suspicious. So the juggler said, well, I juggle them. It's part of my act. The cop naturally was skeptical. So he said, yeah, well, let's see you do it. So the juggler gets out of the car and starts juggling the knives quite proficiently. The cop is very impressed, but somebody drives by at this point and says, oh my gosh, am I ever glad I quit drinking? Look at the test they're making you do now. That was really a stretch, huh? Okay, one more mini lecture for, I think just one more mini lecture for Chapter 25, and then we dive into mass spec and return to Chapter 16. In the meantime, we will see you in class.